Greetings again, ladies and gents. It's time for chapter 20 and time for us to talk about sound. The book starts this chapter with a question. If a tree falls in a deep forest some hundreds of kilometers from anyone, does it actually make a sound? Yeah, it actually asks that, FML. Anyhow, we probably have some idea of what sound is by now, right? It's energy moving through the medium of air. In this case, of course, sound is causing the rarefactions and compressions in the air, which eventually get to your ear, hopefully, and send a signal to your brain that you can interpret as sound. Now, the pitch of the sound, how high or low it appears, depends upon its frequency, right, and also, therefore, its wavelength, like we discussed in Chapter 19 when we were talking about the Doppler effect. Low frequency sounds like foghorns or bass hits have a low pitch and a low frequency. A high pitch, like a whistle or something like that, has a high frequency and therefore a short wavelength. We can hear sounds between about 20 hertz and about 20,000 hertz or 20 kilohertz. Sound below 20 hertz is called infrasonic. We can't hear it. It's outside of our hearing range, just like infrared is just too red for us to see with our eyes. Sound frequencies that we use in like a sonogram or what we call an ultrasound are ultrasonic, and like ultraviolet light, they are just too high for us to hear. Just too short of wavelength, too high in frequency for us to be able to hear, right? Our eardrums are just too small for that, or too large for that in that case. In any case, since waves are energy moving through a medium, sound can't possibly be any different, right? And indeed it's not. We're mostly familiar by now with sound moving through the air. The speed of sound in air is actually pretty fast, what we call Mach 1. It's about 343 meters per second. But sound moves about 4 times as fast in water, something like 1,500 meters per second, or about 1.5 kilometers per second. It's pretty far, right? Talking about over a mile now in 1 second. But that's in water, not in air. A little bit different. So how is it possibly that sound moves faster in water than in air? Well, what does water have more of? What characteristic of water is greater than air? If you said density, the answer is absolutely correct. Water is much more dense than air. And because the particles are much closer together, it's easier for them to transfer that kinetic energy in between them. Now, is the speed of sound faster in steel or in water? And it may be a little counterintuitive to think, you might think that steel, oh, it's too rigid for sound to transfer, and believe it or not, it's not. If you've ever put your ear onto a train track or something like that, you can hear the train coming much, much farther away than you can hear the actual train coming in the air, right? The actual sounds that it's making. Because the steel is much, much more dense. And indeed, the speed of sound in steel is something like 17 times as fast as that in air. Because steel is a very, very dense medium, we can hear the train coming much farther away if we put our ear up to it. Water, of course, is less dense than steel, but it allows creatures like whales to communicate over long distances much more quickly than we can communicate to each other by yelling at each other over great distances. Why? Because water is more dense. Steel much more dense than that, and that's why it conducts sound much better. Now, the real true governing factor, the motivating force for this, the speed of sound being greater in a more dense medium, is this thing that we call the restoring force, or the elasticity. Something that has a structure that wants to keep its shape better means if you apply some energy to it, if you apply some energy to it, something like sound, then as that sound travels through this medium, the crystalline structure, the configuration of the atoms, say in steel, like in a steel rail, like on a train track, the steel is going to want to restore its shape, right? And because it has this strong restoring force, this high elasticity, the energy travels through the steel very quickly. The energy gets passed along from one molecule to another much more easily. And that's why, as a general rule, solids generally conduct sound better than liquids, and liquids generally better than gases or air. Sound, of course, cannot travel at all through the vacuum of space because there is no physical medium whatsoever for the sound to travel through. So, if you watch the movie Alien, right, at the end where Ripley blows the alien, the xenomorph, out of the airlock, you can kind of hear it like screeching. Yeah, you wouldn't, because there's no air in space. And because there's no air, the sound that it would be making in theory, right, the vibration of its vocal cords, if it has those like we have, it wouldn't be able to vibrate the air and cause a rarefaction and compression in order to cause the sound to propagate. Now, light doesn't have that problem because light is its own medium. It's its own crazy particle-wave duality that always travels at the speed of light, which just so happens to be the ultimate speed limit in the universe. But that's the exception or not the rule, so we'll come back to that at a later juncture. Now, as I mentioned before, sound waves are generally made up of two components, what we call a rarefaction, or where the sound stretches the air out, and a compression, where the energy in the sound compresses the air together. And we saw that when we had the slinky, right? If you stretch the slinky out, you pull a little bit of it back, and you let it go, that compression will travel down the slinky, right? And so that's how the air propagates the sound wave. So a compression is just like it sounds, where the air gets compressed, and a rarefaction is the opposite, where it gets stretched out. Now, in order to illustrate this better, let us discuss a hypothetical situation, shall we? And let's see if I can get this better centered. On the board here. Okay, that looks pretty good. So, let's say you have a room, right? And in this room, there we go. So at this one room, you have a window, or this one end of the room, you have a window, and let's say there's a curtain here, right? And at the other end, there's a door. Okay? Now, let's say initially the door is closed and you open the door. What is going to happen? If you open the door, there's only a certain amount of air in this room, right? And this air is going to have to get stretched out, right? The air here is going to get pulled here a little bit, the air here is going to get pulled a little bit, and the total amount of the air in the room is going to get stretched out a little bit. That's a rarefaction, right? What's going to happen? Well, obviously the curtain is going to blow inward, right? When that happens. Now, let's say that we just kind of let the door sit there for a second. At that point, the air in the room is going to equalize, right? The curtain is going to drift back down so that it's vertical, right? And then we decide we want to slam the door. Okay, we slam the door. What's going to happen? Well, all of this air is going to get bunched up and compressed, right? The door is going to close, and the curtain is this time going to get blown outward, right? So the air can get compressed, or if we open the door, the air can get rarefacted. In short, a rarefaction is essentially the opposite of a compression, right? You're talking about some things getting stretched out, like the air in the case of opening the door, or the air getting compressed in the case of closing the door. And if you don't believe me, try this. Let's say instead of having an open window, let's say you close the window, right? And maybe the curtain's still there, whatever. But if you try to slam the door now, all of that air is going to get bunched up and have nowhere to go. So, if you try to slam the door with all of your windows closed, it's a lot more difficult. It could probably still be done. I'm not saying go out and try to break your doors. But if you have your own bedroom, right, with a window in it, try just pushing it closed with the window open and pushing it closed with the window closed. You'll see a very big difference, right? You don't even have to push that hard to see the difference. It's pretty straightforward. Now, sound also does this other funny thing, like most other waves do. They can reflect off of surfaces, right? Which is why, let's say this is not just some small room, but let's say, you know, this is a big lecture hall or something now, right? Let's say you're sitting here and your professor is sitting here, or, you know, maybe you're at the symphony or something, right? And somebody's playing a piano or something up on stage. Now the sound will definitely come to you, but it will also bounce off a wall and get to you. And so it sounds like an echo, right? Or reverberation. And this is why, generally, we don't have opera halls or, you know, places where the symphony plays that are shaped just like basic rectangles. They often have these funny things near the ceiling that help to reflect the sound so that the acoustics are more precise, right? So that the sound gets to you and it doesn't sound like it's hitting you twice or like an echo or like the sound is out of phase. But not all surfaces reflect sound. As you might have guessed, sound will probably reflect more easily off of a solid surface, things that have... Oh, lucky! Things that have a greater restoring force in them, right? Allowing the sound to bounce off of the surface more easily. If you were to, say, take a bunch of egg crates or a bunch of padding and put it on your walls, it would absorb the sound, right? Because as the sound waves move toward the wall, right, where your padding is, the padding can compress and absorb the kinetic energy in the sound. And that's how you can make your room soundproof, right? If you're noisy, if you're like me, you like to stay up late playing video games or whatever, and you don't want mom and dad to get mad at you, just take a bunch of, you know, like the egg cartons, and you can just literally put them all over your walls. And that will really help to dampen out the sound a lot. It's better, of course, if you have something that's sort of shaped like egg crates, but made out of padding. That'll absorb the kinetic energy of the sound a lot better. Now, I apologize for the next bit. I don't have a tuning fork with which to do the next demonstration. However, I did provide a link to a tuning fork demonstration both in the lecture notes and on the Chapter 20 lecture page. At that point, or if you follow those links, you can go and see the tuning fork demonstration that I'm about to talk about. The frequency of something that generates sound, like a guitar string or a drum surface or whatever, depends on the shape of the object, what its elasticity is. You remember the restoring force, the kind of material, of course, that it's made of will have some effect on its elasticity, and so on. For a tuning fork, of course, mostly it's the length of the times, right? That will tell you the frequency. Just like a pendulum, the longer they are, the longer the frequency, or the longer the period, right? And the lower the frequency. So if you took some object like a tuning fork and you smacked it against the table, then it would vibrate at its own natural frequency, the frequency that it wants to normally vibrate at. But if you took the tuning fork and you took the vibrating times and pushed it back against the table, it would go for just a second, right, as the table absorbs the kinetic energy in the tuning fork. But the table will vibrate at the frequency that the tuning fork is hitting it with, not at some kind of natural frequency that the table or the desk or whatever you're pushing the tuning fork into would normally vibrate at. This is what we call a forced vibration. Now, when a system experiences forced vibration at its own natural frequency, then the amplitude of the oscillation can continue to increase. We call this resonance. And it's actually a very simple property. It may sound kind of fancy, but imagine if you're on a swing, right? Now, if you want to swing higher and higher, what do? You have to pump, right? You pull and you push your feet out, right? And that gives you a little bit of torque to increase your swing height, your amplitude. Now, if you were to try to pump like when you're at the bottom, that's going to slow you down, if anything, right? It's not going to make you swing any higher. So what do? You swing when you're all the way at the top and all the way at the top at the other side, and that will get you go higher and higher and higher, right? That's applying energy at the natural frequency of this you sitting in a swing system, right? You have to do it when you're at the top of the swing, at the top of the swing. And if you remember, the period of a pendulum doesn't depend on the mass or the angle, right? It actually takes you about the same amount of time to swing if you're low or if you're high. Doesn't matter, right? But you have to do it with that frequency, otherwise you're not going to swing higher. But if you do, if you continue to add energy to this system at the natural frequency of the swing, you're going to go higher. Well, guess what? It works that way for anything and everything else that can oscillate. So if you have two identical tuning forks and you vibrate one next to the other, it can pick up the vibration, right? Now, unfortunately, I don't have two identical tuning forks. I don't even have a single tuning fork, because you don't have a tuning fork sitting around your house unless you're either a physicist like myself who needs to make a video for his students, or you're a musician, right? Somebody who works repairing pianos or something like that and needs to generate a certain tone many times. But if you did have two tuning forks, and you struck one and oscillated it close to the other without even touching, just vibrating the air, the other tuning fork would pick up the oscillation and begin to oscillate. Why? Because one is putting out energy into the air at its natural frequency, and because the other one has the same natural frequency, it's going to pick up on that energy and start vibrating. Unfortunately, this is why for many, many moons, since time immemorial, for a long time, we've realized that if you wanted to march an army across a bridge, you have to make them break cadence, meaning they have to stop marching in time. Because if they all vibrate the bridge at the bridge's natural frequency, it will cause the bridge to fluctuate, right? To accelerate. And that can be enough to knock a bridge down. Now, believe it or not, this has happened in even more recent times with this thing, the Tacoma Narrows bridge. And that was not even that long ago, about 100 years ago. No, yeah, it was 100 years ago, I think. It was 1918? I could be wrong. Anyway, I provided a link in both the lecture notes and on the Chapter 20 lecture page. Now, the phenomenon that actually caused the Tacoma Narrows Bridge to fall was this thing we called aeroelastic flutter. And basically, because of the dimensions of the bridge, its length, its width, whatever, when the air passed under and over and through the bridge, to grandmother's house we go, What happened is it started to vibrate at the bridge's natural frequency. And as the wind picked up on this one day in particular, it just kept increasing the oscillation, which kept increasing the amplitude, and eventually, what happened? It fell. It wrecked, right? If you watch the video, there's a car that's kind of stuck out in the middle, and the legend goes that there was some professor who was driving across the bridge, left his dog in the car, and he freaked out and got out of the car, figuring that it was going to stop. And when he realized it wasn't going to, he had to go back to the car and get his dog and get off the bridge before it collapsed underneath the both of them. Crazy story, but true. And not even that long ago. And that, ladies and gentlemen, is why we have to know our history so we learn from our mistakes. And if only certain people would learn from that, we might not be in this crazy predicament that we're in now. I'm not going to name any names or point any fingers. It's not any of you, however, so keep it up. Now, if sound waves interfere, we should hear some evidence of that, right? Let me ask that another way. If waves cause interference patterns where they overlap, sound waves should interfere as well, right? Well, I've included a link to this thing called a tone generator, and basically you can choose the frequency of the tone generator, and you hit play and it'll make a single sine wave oscillation, a single tone, ooh, like one sound, right, at one frequency. Now, I'm going to draw you a little bit of a diagram here, okay? Let's say that we've got some sound signal, right? Some woo, some single tone. And we've got some other one, woo. And these two are at very different frequencies, right? We can very clearly see that this one is a much shorter wavelength than this one. Where can we be sure that they will overlap? Well, maybe overlap is not the right word. If the sound is, let's say the sound from this one is coming out of one speaker and the sound from this one is coming out of another speaker, they're going to overlap in your eardrum, right? Right here. And so you're going to be able to hear if there's any kind of constructive or destructive interference in theory, right? Now, let's say that we've got two waveforms that are maybe a little bit closer, right? But not quite the same. Let's say that this one is 440 hertz. And let's just say, for the sake of argument, that it starts at the same place that this one does. And this is 441 hertz. Now, most of the time, these waves are not going to be in phase anywhere, right? Nowhere. These have different wavelengths and different frequencies, and so they're, as this one's, even if they start with this one going up first and this one going up first, they're not going to be in phase for a very, very long amount of time, and they're going to get further and further and further out of phase, and then they're going to get closer and closer and closer into phase, and eventually at some point right here at the very end, they're going to be back in phase, right? Because in 1 second, this has to complete 440 hertz or 440 cycles. This one has to complete 441 cycles. And when they're done, when these patterns complete, they'll be back in the same place again. So, these two waveforms will only be in phase once per second, right? So, if you open up the tone generator and you start at 440 hertz, you press play. You open up another tab with the same tone generator, right? You just copy paste the link again. And you put it at 441 hertz and you hit play, you should hear a whoop, whoop, whoop once every second. 1,000, 1,000. Every time it goes whoop, whoop, it'll be once a second you'll hear a beat, right? What does that sound like? Well, let me just show you. This is 440 hertz. 1 hertz. Interesting, right? I'm going to make them stop here for just a second. Now, I want to pose another question to you. What if we have another waveform here, and let's say this is 442 hertz. Let's just get rid of this one altogether, shall we? Okay, this one's 442 hertz. When are these going to be in phase? Well, you can make the argument that by symmetry, this is going to complete 220 cycles here in the middle, and this is going to complete 221 cycles here in the middle, right? That's an even number. And so right here in the middle, they'll overlap or be in phase again, and then they'll be in phase here again at the end when this 440 and this 442 hertz completes. Let's see if that's true. I'm going to change this one to 442 hertz, and this one will be 440. What happens? Now it's twice a second, right? If I change this one to 443 hertz, it's 3 times a second. 444, 4 times a second, and so on. We call that this sort of funny name, a binaural beat. And the number of beats per second that you hear is the difference in the frequency. I urge you to try to test it out. It's actually pretty interesting. Thank you for watching. I hope you've enjoyed this video. Stay safe.